Okay, so I'll go ahead and get started. Everyone should have taken the pre-lab quiz and turned in the lab from last week. Like I said, this should be a shorter lab. It's called Lab 7, and we're going over conductivity, salinity, and desalinization. Again, obviously you won't be doing the lab, so we have it's like a 10-minute YouTube video of someone else going through the lab. It's not someone in our department, so it's a little different, just the setup that they use versus the one we would have used, but it's still the same basic principles. They're going to be making a distillation. The lab starts on page 60 if you want to follow along at all. There's some graphs in there, but they will be, the images are basically the same ones you're going to see on the PowerPoint slides. So, okay, so Lab 7, this is just the outline of what we're doing. Your deliverables for this week is, all you're going to have to turn in is there is questions on pages 66 and 67. But I think the Word document that we're giving you, you can just type straight on there. So you can just, once you complete the Word document, you can just turn that in so you don't have to fill in the graph manually. So salinity is just the amount of salts in a water. Normally, when you think of salts, you think of table salt, sodium chloride, NaCl. But when we're talking in terms of water quality parameters or water quality, salts is going to be any sort of ion that's dissolved into the water. So it can be magnesium, sulfate, calcium, anything like that. And then your salinity is the percentage. And this little symbol right here is not just percents. You have your percent sign, and then this little 0 means that it's parts per thousand. You've probably heard of parts per million. This is just parts per thousand. So the way that you determine that is if you were to take 1,000 particles of whatever water sample you have, if it was fresh water, then less than half of a percent would be salt ions, if that makes sense. And then, so I think that would be 50, it's either 50 or 500 parts out of the 1,000 would be your salt ions. So for fresh water, it's got to be less than 0.5%. Brackish water, it's just a mix between salt water or seawater and fresh water, and that can be anywhere from 0.5% to 30%. And then seawater is generally around 30, but you'll see kind of in the lab today that fluctuates just based on the amount of water, fresh water that's input into it. And then brine is going to be any sample that has over 40% parts per thousand of salt ions. And then you can see kind of here on this map, up here you would expect fresh water, here would be more brackish. You can kind of see a difference in coloration. They're not completely mixed because this is, obviously this is San Francisco, this is the bay, and so you have freshwater inputs mixing with salt water from the ocean, so it's not going to be completely, you'll see in the data we give you today, it's not going to be completely 35% salt water, but it's not going to be freshwater either because there is a high concentration of salts in there as well. So if you've ever seen the show Moonshiners or anything like that, you might be familiar with this, but this is just a distillation setup. This is a very simple one. This is how we would have done it in the lab. You would have had your heating source. In this case, it would be a hot plate. And what we would be doing in this lab is basically desalinization. So we would have taken, I believe it was water from Ocean Beach, seawater samples. You would have put it in this distillation. You'll see this in the video. And then you'll put boiling chips on, and you have this tubing with a rubber stopper. So as you heat the water up, the water vapor, which ideally would be just pure water vapor, would come up through the stopper down the bend, and then it would collect. The water vapor would go downhill into this collection vial, and this would have water packed around it to have the water molecules recondense into water. And ideally, what would happen is you're taking all of the pure water ions out, and then what you're going to be left with is all those salts. So this, let's see, I think the next slide actually has. You'd have to make sure that this is not too close to your distillate. Your distillate is going to be just some terminologies. So your distillate is going to be what you actually collect. Your brine is going to be, so your brine is going to be your extremely concentrated solution once most of the water has been taken out and purified. The purified water is going to be your distillate. The brine is going to be your extremely salty, what's left over in your Erlenmeyer flask. And then seawater is obviously going to be what you started with before the heating. And then you'll just need to know those three terms for when you're doing your questions. If you need it on the graph for graph A, it kind of breaks it out for you. It says seawater and then parentheses initial and then brine parentheses in flask after distillation. And these graphics are in your lab manual for you to refer back to as well. Brine, hypersaline. So desalinization is, a lot of people are thinking that might be the way to fix California's drought. Unfortunately, it is an extremely energy intensive project, and it takes a ton of money to do it. So this is just kind of step by step how you take ocean water and make it into clean drinking water. You need to pump the seawater from the ocean. Obviously, they put little screens on to try to minimize the aquatic life that they suck in. Obviously, they get bacteria and phytoplankton and things of that nature, but the larger fish and creatures mostly are saved. Pre-treatment, they just filter out all of the smaller animals that get stuck in it, your bacteria, viruses, and anything that they pull out is sent to the landfill. Then they desalinate it. According to this, they get more than 99% of the salts and minerals removed. What they remove is they can't put it straight back in, so they mix that with wastewater, and then the wastewater and brine mix is then resourced back into the ocean. The clean fresh water is now taken to do post-treatment where they chlorinate it, depending on where the water is. Each city that you go to will have different tasting tap water, and that's just based on the minerals present. So most of the time, if they are going to desalinate water, they want to have it taste as close as possible as the natural drinking water. So they will put in a mix of minerals to make it taste like you would normally get from a tap. And then, of course, you have to store it and deliver it to homes or schools or any sort of buildings. You need to put ions in your drinking water. You can't we use deionized water in the lab a lot just because there are no ions in it. It's just pure H2O. And if you wash things with deionized water, you won't get any of these minerals right here that is naturally present in waters. And those will mess up your readings a lot of the time on a lot of the instruments if you just use tap water, because if you're measuring conductivity, like we would have been doing in this lab, if you have a lot of sodium or ions in there, you'll bump up your conductivity. And if they're sitting on the meter before you use it, then your sample is already compromised. but we do need electrolytes is also another way to just say ions. So these are some of the health benefits that electrolytes use. That's why if you're doing sports a lot, you mostly want to use a sports drink like Gatorade or Powerade or something like that, because it does give you healthy electrolytes and you can recover faster. Electrolytes help your body conduct electricity or energy, regulate fluid balance, transport nutrients, support proper muscle function, support mental function, and help convert calories into energy, regulate pH, and then they have a couple more things. And then obviously we cannot drink seawater, but a lot of marine birds and mammals can drink seawater. The main difference is that they have something that's called a salt gland. So I won't go deep into the chemistry or the physiology that allows them to do this, but basically they drink in the seawater, and then up here around their eyes they have what's called a salt gland, and it just filters out the salt from the water, and then the salt gets a really briny, salty liquid, and it just flows down. And if you can see this tiny hole on the beak, that's where the salty liquid flows out, and they excrete the salt from their bodies. So that's really all there is for presentation. So now we just need to watch the video. So everyone can watch this again if you choose to on your own time. If you need to pull from this video for some of your questions for any reason, the YouTube link is here on Lab 7 page. So you would just go there, and then it's right down here for everyone. If you can't hear it, let me know.
We can't hear it.
All right, you can't hear it?
There's no sound.
All right, hold on. Let me stop and then see. All right, let me know if you can't hear it now.
Over 70% of the Earth's surface is covered with water. But most of that water is salt water in the oceans. Only a very small amount of that water is actually fresh water, and most of the fresh water is locked up as glaciers. And some of it's in our lakes, and only a very small amount is in our streams and in groundwater, and that's the water that we rely upon as drinking water. The leading cause of death of children in the world is lack of clean water. So can we take salt water and turn it into fresh water? That's the purpose or objective of this lab, to take salt water and run it through a process called distillation and distill it into fresh water. Process of distillation is very energy intense. We're going to need a Bunsen burner for this lab. We're going to need obviously a lighter to start the Bunsen burner. You'll need a 250 milliliter Erlenmeyer flask with a rubber stopper and a tube coming out of it that's going to collect the steam And you're going to need a test tube in order to condense the steam into liquid water. You'll need a 600 milliliter beaker, some ice, a couple boiling chips or rocks, LabQuest device, and a conductivity probe to measure how much salt is in the water. And of course you'll need salt water in order to run this experiment as well. To your 250 milliliter Erlenmeyer flask, go ahead and add a small handful of rocks. And those are going to be boiling chips that are going to allow the salt water to boil at a normal amount without overboiling. To the Erlenmeyer flask, also add 100 milliliters of salt water. Replace the cap on the Erlenmeyer flask. Make sure that the tube, the rubber tube, is going to travel continuously down without having a bend or a kink in it where the water can start to build up. That can be kind of dangerous, so make sure it's a normal line going all the way down into a test tube, which is and this test tube has to be extremely clean because you're going to be collecting clean, pure distilled water, so make sure that this is very clean. If not, make sure to rinse it out a bunch of times with distilled water and collect it in a 600 milliliter beaker that contains an ice water bath. So this beaker should contain ice and water to make an ice water bath. Okay, so there's your ice water bath. Go ahead and put the test tube in the ice water bath. Before you start the experiment, you're going to want to measure how much salt is in that water. I made up the salt water to contain 8 grams per liter. Now let's use our conductivity probe to measure and see how much exactly is in there. Plug your conductivity probe into the LabQuest device. Over a towel, rinse the conductivity probe with distilled water. The tip of the conductivity probe, the very end of it, rinse it with distilled water. Only ever use distilled water. If the distilled water ever runs out, make sure to only fill it up using the distilled water in this container and not to fill it up from the sink, so that these always only contain distilled water, purified water. Place the rinsed conductivity probe directly into the salt water. Make sure that the tip of the conductivity probe is completely submerged. Right now it's not, so what I need to do is tilt this a little bit so that the conductivity probe is completely submerged. Make sure the toggle switch on the conductivity probe is on the 0 to 20,000 reading. This is because we're measuring salt water, and salt water is going to have a high reading. So we're not going to use either the lower readings, we'll use the highest reading. On the LabQuest, change the units to milligrams per liter. Change the units to milligrams per liter. I said before that I made this salt water as 8 grams per liter. That would be 8,000 milligrams per liter. This is reading 7,215. That's probably pretty accurate. Simply record the live readout in your data table. So I would write 7215 milligrams per liter in my data table. You do not need to connect your iPad to the LabQuest for this experiment. Carefully remove the conductivity probe from the salt water. Over a towel, rinse the salt water off the conductivity probe using distilled water. Set the LabQuest aside. You won't need it until you've completed the experiment. Reset your Erlenmeyer flask. Put the cover back on. Put on a sweet pair of goggles. Now it's time to light and adjust your Bunsen burner. So first thing you want to do is connect the Bunsen burner tube to the gas. Turn the valve on. Go ahead and light your Bunsen burner. So this flame looks pretty good, but I'm going to show you how to make a couple adjustments in case it doesn't look so good when you first turn it on. First of all, I'll show you that there's two adjustable things you can do. One is that you can turn this, and by turning that, it's going to reduce or increase the amount of oxygen that's going into this thing. All right, so if you find a really orange flame, this is what you need to adjust. You need to adjust the base here. Get it back down so you have basically a flame within a flame. You've got the inner blue flame and the outer blue flame, and should be about a 1-inch flame there and about a 2.5-inch flame there. If you're not getting enough flame, you can do one of two things. You can make this adjustment on the base here. Maybe that's it. Maybe that's reducing how much gas is coming out. By increasing this, you're increasing how much gas is going through, and that's way too much. Again, you just want kind of a normal flame there. So again, that looks pretty good. I'm going to be happy with that. Just wanted to show you some adjustments quick on the Bunsen burner. Go ahead and begin heating your salt water, making sure that everything looks good. Okay, this tube should be going all the way down without any kinks in it, all the way into your clean collection test tube, which is in the ice water bath. You want kind of a nice medium controlled flame so that things don't get out of hand. If they do get out of hand and this boils over too much, you're going to contaminate your test tube, and what you're going to want to do right away is if things get out of hand too quick, the first thing to do is probably just to move the Bunsen burner out from underneath the flask. Then obviously, then you can start taking time and making adjustments on the flame. So things are going pretty well. I've got a pretty good rolling boil here. Just be careful that you don't want it to boil all the way up to the rubber stopper, or you're going to start to get salt water in there. So again, you can make some minor adjustments on the flame to make sure to keep it down so that you're not going to get too hot of a boil, just a normal boil. You can see I'm kind of zooming in on the test tube inside the beaker, that you can see that the level is rising. I'm collecting distilled water as it boils here, slowly but fast enough that you can observe it happening here, and we're condensing the steam into water here in the ice water bath. Again, just be very careful. This is a potentially dangerous situation, so please just don't sit on your iPad and play games. Obviously, you never want to do that, but this is something you need to keep an eye on here. We got very hot steam, we've got boiling water here, we've got a potential pressure situation if this gets backed up, so just make sure you're monitoring this the entire time it's happening. When it looks like you've got enough distilled water collected in your test tube, go ahead and shut off the flame by turning the valve off. Don't just blow it out here, the gas will still come out. Now what we really want to do is get a reading on what's the conductivity of the distilled water. So again, you might burn yourself if you grab that, just be careful. And we want this to be in room temperature water, not ice water, so I grabbed another beaker. I'm going to fill that up with, carefully so that you don't burn yourself, transfer your distilled water into that room temperature water. When a few minutes have gone by, place the conductivity probe inside the distilled water test tube. Since we're reading distilled water, you really need to change this setting. Okay, so this should no longer be 0 to 20,000. We're checking distilled water. That's probably going to be a pretty small amount of salt in there. I'd probably change it to the lowest setting, which is 0 to 200 for this reading. Make sure that your units are in milligrams per liter. And I'm now reading 11.5 milligrams per liter, where we're reading in the 7,000s before. So yeah, we definitely purified and distilled the water, the salt water, and obtained some very fresh, pure distilled water. Clean up, make sure to rinse off your conductivity probe one more time and dry it off before you put it away. Like always, rinse out test tubes and beakers. I just recommend at least rinsing them thoroughly 5 times to make sure you get any salt or anything like that off of them. Certainly allow your Erlenmeyer flask to cool for a long time before you touch it. Please take your time.
So that's the exact lab that we would have done. The only few differences is that we would have used a hot plate instead of a Bunsen burner. And the units that they measured conductivity in is milligrams per liter. You don't really need to know this that much, but that translates exactly to parts per million. The we would have measured conductivity with the same exact probe, just it would have gone to the Hawk meter that we saw a video of yesterday or last week. So they measure conductivity. I'll briefly go over what conductivity is. You might have heard it if you've taken any sort of physics 2 or electrical circuits. Conductivity is just the ability to carry an electrical current. When it's relating to water, it's the more dissolved ions you have in a water sample, the higher your electrical conductivity will be, which means that the easier it will be to carry an electrical charge. The units for conductivity is usually it's in Siemens. The readings that they got out was in micro Siemens. We would have either used millisiemens or micro Siemens. You'll see it'll be called out on the data sheet that you download which unit it's in, and then you measure conductivity because you can't technically measure salinity. The way you get that is all those meters, that one did not calculate salinity, but the Hawk meter that we would have used would have taken the conductivity and done some complicated formulas, and it would have given us a salinity reading as well, along with temperature. So those are the three main parameters that we would have been using in this lab. And then, so that was part A. If we were to actually do the experiment, part B would have been, there's 4 different types of water samples: the seawater from Ocean Beach that we would have distilled, lake water from Lake Merced, tap water, and deionized water. And while you were heating up your distillation, you just would have done conductivity readings of those 4 samples and written them down in the chart on page 67. We'll obviously be giving you those data as well. And that would just be to see the different readings that you would get from different sources of water with different salinities. So on page 7 right here, it says download Word doc with data to use for this lab. That's where you'll be getting your data this week. You'll just be downloading that. And let me share that with everyone. Once again, you'll have enable editing up here. You'll just have to click that before you can use anything. Does anyone have a problem downloading it or finding the data set? Okay, so it's up to you. If you want to write the questions on this Word document and just turn in the Word document, I believe you can do that. Let me just see if it's set up to take Word documents. It should be able to, because it says you just need to turn in a file upload. So if you want to just work completely off of this document, that's fine. If you want to copy the data over into the charts on page 66 and 67 and answer the questions and take scans of those, either one's fine. Just make sure if you do it on the Word document, you type out the questions and then answer the questions below them, just so I'd know exactly where you're at. Just a couple notes before you really get started on the lab. For part A, all you have to do is describe, it says in your own words, describe in a couple sentences the distillation procedure you used. Just describe the distillation procedure that you saw in the video that you would have done. Part C, it goes over dilutions for taking samples of brine. Don't worry about that. You don't need to answer that. You can just skip that. And then you will need to answer the 5 questions on page 67. For number 3, it says, how does your measured salinity for Ocean Beach water compared with the global average for seawater, parentheses, salinity equals 35 parts per thousand? So when you get to that part B right here, you'll see Ocean Beach salinity is 27.2. Here's a little visual to kind of, I touched on it briefly before, but here's a little visual. So hopefully everyone can see this. If not, let me know, but you should be looking at a map of California, and here's San Francisco Bay, and here's Ocean Beach. This is of all the rivers and the watersheds. So if you can see my mouse, all of these rivers that I'm circling all drain right here into the San Francisco Bay. So when it rains, that's a huge amount of water that's rushing into the bay. So use this visual to kind of help you answer question 3. And if you need to, I can show it to you again, but I'm going to switch it back to the data. But really, that's about it for this week. It's just, you're going to be answering those 5 questions on part B, and then just writing the description of distillation in part A. And then that's all you'll need to turn in for this week. There will be a pre-lab quiz for next week. That'll be open. I'll open that right now. If you, for some reason, want to take that tonight so you don't have to worry about it, it will be open. Just don't forget to do it before next week. And then this lab will obviously be due next week before class starts.